Welcome back to Wood Engineering. I'm Jeff Orochko from Carleton University, and in this video we will be talking about different kinds of wood structures and what wood structures look like and what different opportunities there are for wood structures and what's the state of wood construction these days. And this presentation is kind of a slideshow more or less, so there's going to be lots of pictures. Okay, let's get started. So all the different types of wood structures that we can have. The most common being light frame construction, which we're all pretty familiar with. 2x4 joists, 2x4 studs or 2x6 studs, and sheathing on top and wood joists. Like basically the way that a large majority of house building is done in Canada. Then we have heavy timber construction, which is more what we're interested in this course, which is kind of the future of timber construction, where we are looking at large timber members, we're looking at timber walls, we're looking at big glulam beams. What kind of neat structures can we build out of heavy timber? And then at the end, we're going to talk about as well different kinds of construction that take advantage of the advantages of different kind of materials, including timber with steel, timber with concrete, and different ways that we can leverage those strengths to make new and exciting kinds of structures. So starting with light frame construction, this is what I was talking about. Probably most of you have seen something like this before. This is what house construction typically looks like, in Canada at least, made of light frame construction, where the walls serve the purpose of resisting gravity loads, but they also are the primary lateral force resisting element for earthquakes and winds. And the way that they resist those forces is by putting sheathing of OSB or plywood sheets nailed to the outside of all of these vertical wood studs. And those stud cavities, the spaces between the studs, are also a good place to put some insulation, which of course is important in Canada. Just makes this system extremely popular for housing construction. And we have members spaced very close together. The wood is made of, the roof is made of wood, the walls are made of wood, the floors are made of wood. Basically everything is made of wood. Now there are two ways to go about light frame construction. One is this platform construction, which is probably most common, because what you do is you put up first story walls. Okay, so you probably start with some kind of concrete or masonry foundation. You put a bottom sill plate connected to the concrete, and then from there you build a first story wall made of these studs, probably 2x6 studs. Then you build a floor level on top of those studs, so you can see the edge of the floor here, and here are the floor joists, also made of timber elements. These days, probably even more common to see wood eye joists here instead of just straight up 2x6s or 2x8s. And then on top of that floor, you build the next level. So that's why it's called platform, because you build a wall, then you build a platform, then on top of that platform, you build a wall. So that makes construction very easy because you just build one story at a time. And you've got a automatic nice fire stop layer here where you have the floor interrupting the cavity of the wall. So fire can't go into your wall and then go from the first story to the second story directly because there's a stop. Makes very easy working platforms. So you already have a floor here so that when you work on the second story, you've got something to stand on. And the disadvantage of this is if you go back to shrinkage video, we're going to get more vertical shrinkage in this system, which is not such a big deal for two-story structure, but maybe for a 5-6-story structure, this could become a problem because now you have vertical elements have the very little shrinkage because longitudinal shrinkage is low. But then you have all of these opportunities to have elements that are put on their side so that we have perpendicular to grain shrinkage, which as we know is very high. To get around that, you can do the alternative, which is called balloon construction, which basically means you build the walls first, and then you hang the floor from the side of the wall. That's balloon construction. That applies to light frame construction like this. We also use these terms platform construction and balloon construction in CLT type construction to talk about the ways that the walls are connected to the floors as well. But so when we're talking about light frame, it just means you build the walls first, then you probably have some kind of ring member that goes around the outside, this ribbon member here that connects to the side of the wall, and then you build the joist into that. So now you can use longer studs, which can be convenient, but they could also be difficult to handle. It's more difficult to erect because now you have to erect a 2-story high wall every time you do a wall, but it reduces settlement. And that means if you have a masonry veneer on the outside, which is also very common in Canadian homes, you don't have to accommodate as much movement in that veneer on the outside, which is nice. And it's harder to do the fire stop. So where do we see light frame structures? Mostly single family and multi-family residential. So, you know, single family houses or, you know, semi-detached or attached housing. And this is what it looks like. You know, everybody knows what houses look like, but, you know, that's a house, you know, without its clothes on, so to speak, on the right. So you can see all the studs on the inside, and on the outside here is an OSB sheathing, which is a common material to use for nailing to the outside of this wall, which also provides lateral resistance. Here's what multifamily residential might look like, also made of light frame timber. The thing about most of these buildings is that you know, you wouldn't really know that it was made of timber if you didn't know, because all of the exterior finishes are not typically timber. They're going to be masonry or siding or something like that, or stucco. And on the inside, you know, we usually have some gypsum, so you don't really ever see the timber. So obviously the major reason why they use timber in these houses, and we're using light frame lumber construction, is because it's cheap and very easy. So that's why, you know, 90% of houses are built that way. The application for light frame in commercial is only growing because of building code changes allowing, you know, up to 5-story structures made out of light frame construction. So we're going to see a lot more of these larger structures being built out of light frame now and in the near future. So this is what they mean by tilt-up construction, which I think I mentioned earlier. So basically you can build the floor, you can build the walls on the ground horizontally and then tilt it up. And of course, I love this picture, which is from the old school Canadian Wood Council slide set, because of the outfits these guys are wearing, which are great. You got the huge bell bottoms. But they basically build the floor on the ground and then they lift it up and put it into place. Also, with this kind of construction, you can build the roof out of roof joists manually, or there's a big business in making prefabricated roof trusses, which you can then just lift into place, which makes it very, very easy. Of course, the roof is kind of the hardest part geometrically because of all the typical angles that you see in sloped roofs, especially in Canada. This is a detail you've probably seen in your basement before, which is called bridging. You know, if you happen to have a basement and you can actually see the joists, the bridging in between prevents lateral torsional buckling of these beams, which we will talk about in much more detail when we look at bending design for these members. But basically what's happening is the top of this member is being braced against the bottom of the next member. So, you know, in lateral torsional buckling, if you're pressing down on a beam, the top wants to buckle out to the side. So in order to prevent that, we put this bridging here. You can also do this by putting a block in here, like a solid piece of, if this is a 2x10, you put a solid piece of 2x10 and then toenail it in on the edges to prevent that sideways lateral torsional buckling. Here's what the full framing for a house like that looks like. This is quite a large structure, but it's just everything open up. You can see the windows. Over the windows, you need lintels where you just turn the member sideways. Over the doors, you need lintels, etc., etc., etc. And this is a close-up of what the plywood sheathing looks like, but we already kind of saw that before. Okay, so in detail, a light frame wood shear wall looks something like this. And just for the purposes of terminology especially, we have our studs, which we've talked about already, which are the vertical elements, especially the ones that are in the middle of the wall. At the outside of the wall, those studs are typically called chords. And they're called chords because they will typically take tension and compression. If I try to push this wall off to the side, maybe if I push it this way off to the side, then the wall is going to want to rock. And that means that one side of the wall will be in tension and the other side is going to be in compression. So those cords are designed for those forces. And then we have to connect the wall to the foundation. So we can have cast-in plates bolts, or we can have drilled-in bolt anchors. And those are typically connected directly to these cords using some kind of angle bracket. The bottom plate here, if it's onto the foundation here, they'll call that a sill plate because it's the sill of the wall. And at the top, they'll call that a top plate. And often that one may be doubled. Then to provide the actual lateral resistance, because obviously if I push on this wall without the sheathing, you know, these connections here are not designed for moment. So the whole thing will just turn over. So what we need is to put plywood or OSB on the outside of the wall and nail it into the studs and the sill and the top plate so that it is what provides the in-plane resistance to lateral forces. And we'll put edge nailing, and we can calculate exactly how many nails we need and what the spacing should be and what the size of them is. We won't cover that in this course, but we will cover nailing in general. So moving on to heavy timber construction, this is a very nice picture of a historic building in Toronto at King West. And this is what the old heavy timber construction would look like. So there's a lot of buildings like this in Toronto, Vancouver, I think in Vancouver, also in Ottawa, where basically it's a masonry structure. So all of the exterior walls are masonry, unreinforced masonry, and the interior gravity frame is all heavy timber. So we have really heavy columns and heavy beams with these little cap plates and joists to hold up the floor. And this is just a very common way of designing. So the lateral forces are taken by the external unreinforced masonry walls, and the vertical forces are all taken by the wood. And this is still what we can do today. And it's, you know, if we exchange especially if we exchange the masonry for reinforced masonry or for concrete, then we can still do gravity systems out of wood like this very easily. And of course, it looks beautiful. You know, whether this structure is going to behave very well in an earthquake because the unreinforced masonry, you know, is not exactly sure, but it's nice inspiration for the look, certainly. So if we want to do this in a modern sense, we can do post and beam construction like this. And we still have heavy timber, but the connections are quite a bit different than they used to be. So now we can use steel plates, nicely designed steel plates with either bolts or nails or timber rivets, which are what are here. Here you can see some bolt holes to join them all together and make a really nice look. And you can see what the connections might look like. And on the right, you can see in comparison to light frame timber, which had all the members spaced close together, in heavy timber post and beam, the beams and the columns are separated quite far apart. Here's some more example of what post and beam might look like in general. Now, since post and beam now doesn't have moment connections generally at the end of these members, because it's next to impossible to make moment connections out of timber, we need some other lateral force resisting system. So that might be bracing, diagonal brace, could be like cross bracing like this. Often in older structures, you might see some knee bracing like this. Or we could combine heavy timber, post and beam, with some other element to make a shear wall, just like in the masonry building that we looked at that was the historic building. So in this case on the left, we have a concrete shear wall, and the rest of the structure, which only then has to resist gravity, is made out of heavy timber, which is you know, very beautiful. Can also use some infill walls. In this case, these infill walls will not be structural, presumably, but that would be another way to do lateral resistance, would be to build some kind of infill wall within the beams and columns. Then, of course, going past post and beam, the new trend in timber construction is to use mass timber panels, which is just basically huge solid wood walls, which sounds crazy if you never really considered it before. But actually turns out that these are pretty easy to make, I mean, with specialized equipment, but they have a lot of great advantages. Really high strength, and much easier to erect, and you can prefabricate a lot of it. So it's like putting it together like like pieces of Lego, and also quite beautiful. And you can build quite tall with them. So this is kind of the new hotness in terms of timber construction. And we'll look at some examples of those kind of CLT buildings and what you can do with them. But if you want to then combine all of these different things, you can combine post and beam with CLT. Here's two different ways that you could do it. CLT is the cross-laminated timber is a really nice material to use for floor slabs because it's really easy to put them down and join them together, and you don't need any heavy equipment to do that. If you want to put in a concrete slab, you need a lot of heavy equipment to do that. You need to pour the concrete, you need to have all the studs, and you need to have all the forming available and all that stuff. But if you just want to put in a CLT, you just bring it to site and you lift it into place and you put it in with basically screws and a drill that's not much bigger than, your regular kind of drill that you have in your house. So that's a nice way to do a structure with glulam, post and beam, and CLT on the left. On the right, another way is you can use the CLT to do the lateral load resistance, because it's really excellently natural for that, and use glulam beams for the rest of the gravity frame. And here looks like the top of this is not CLT, but probably some kind of poured floor. Here's another way that you can do it without using the beams. This is Brock Commons at UBC. And this is a really neat system because basically all they have is columns and slabs. So there's no beams in this building. And they came up with a special system to be able to do it. I mean, in order to be able to do that, they had to space the columns quite close together. But since this is a university residence, and if many of you are familiar with university residences, know that the rooms are not necessarily that huge, so they can afford to put the columns quite close together. So that made for a really easy way to erect a building, and they can do that basically super fast and also super quiet. Now, if we want to combine heavy timber with other materials like steel or concrete, here's some examples of steel. You're building a steel building, but why not use a CLT roof? It's very easy to put in place and has a lot of advantages with construction. So this must be, and also if you can manage to make it visible on the interior, then you get an aesthetic benefit as well. On the right, we have what's basically a steel frame with infill light wood walls and floors. So the main structure is out of steel, but then all of the dividers and stuff are made out of wood. This is not very typical because usually they'll use light gauge steel for the interior walls in a steel building, but this is certainly probably cheap. Some more steel and wood examples. Steel and wood is kind of a really natural pairing, which is how kind of I got into wood in the first place, starting out as a steel kind of guy, because there's a lot of ways that you can combine steel and wood together and make things that actually look very nice. So you can see it's like a kind of a bus station on the left with nice steel columns to provide all the lateral load resisting system, but a really nice attractive wood roof with glulam beams and what's called a GLT deck, which is a glued laminated timber, which is like CLT but only in one direction. And on the right, combining the other way around, making the columns and slab glulam and CLT, but with steel beams to probably increase the span or stiffness or something like that. Here's one where the lateral load resisting system is in steel. So we have steel braces and wood infill and glulam beams and CLT floors. So really what we're looking at here is just what are the kind of exciting opportunities that we can get by combining these materials together. Steel is a natural light system for doing lateral load resisting, and especially here, these are buckling restrained braces, which is a high performance earthquake system. So you can get the benefit of that high performance earthquake system, but at the same time get the other benefits of wood in terms of constructability and aesthetics and lightweight. Concrete is another thing that is combined with timber very often, and the reason being that in the early days of CLT, you know, people are a bit gun shy about making the elevator cores and the primary egress, like emergency exits, out of wood because it is combustible. Now, there's definitely ways to get around that, mostly involving encapsulating those timber elements in heavy layers of gypsum. But in order to get some of these early projects like Brock Commons, which is the same building we talked about earlier on the left, in order to get these projects through approvals, in order to be able to build a huge, tall timber building like that, then they decided to make the primary core, lateral load resistance, and emergency egress out of concrete walls. So then there's no question about how well this structure will perform. Another thing that you'll notice here is the first story is made of concrete. It's a concrete frame. The reason for that being, at that first story, then they can space the columns further apart. So if they have assembly spaces or retail or something in the first floor, they make that out of concrete, and then the rest, where they can afford to have these really closely spaced columns, they made it out of timber. And that's a very common thing to do as well, is to make a first story podium out of, like a commercial area out of steel or concrete, and then make the rest of the building out of timber. On the right is another example of a concrete wall just connected with some glulam beams, which looks very nice. Okay, here we have another thing that's being done and researched a lot these days, is to combine CLT floors with a concrete topping. And the reason for this primarily is for stiffness and also acoustics, because one of the problems that has been found with the CLT floors is that since they're very stiff and light, they can transmit sound. For example, walking sounds through, and adding the weight of concrete and that material on top can help to mitigate that problem. It can also help to increase the spans of CLT floors without increasing the thickness of them too much. The benefit here is, we have to make some connections between the CLT and the concrete, which we can do with, in this case, some screws that are just screwed into the CLT. But the natural thing here is that the CLT then becomes the formwork for the concrete. So it's very easy to do as long as you can just set up a proper edge. So if I want to select a system, I mean, there's lots of exciting opportunities. Everything is usually going to come down to cost. Obviously, when you're talking to your run-of-the-mill owner, the important thing, I guess, when you go out is to look, if you're interested in this kind of thing, is to look for opportunities where you get owners or architects who are interested in doing something special. Just because in the early days, developing the expertise of people in the field is a bit of a challenge. So, but once we get more of those structures, and in the last 5 years or so, there's been many, many more very interesting wood structures being built in Canada and all over the world. These things have begun to become more cost effective. And the other thing is that the industry associations, like the Canadian Wood Council, have been doing a lot of studies to do direct cost comparisons between, what does it cost to build something out of wood versus what does it cost to build something out of steel, so that they can take advantage of things like the improved construction time that you get with a lot of timber structures, especially relative to something like concrete, so that you can put your building up very fast, which has a an effect on cost, right? Which is what schedule means in the second one. What's your building being used for? What are the code requirements? The other thing that's affecting wood construction right now very much is the rapidly changing codes in this area. So now more of these things are included in the code and permitted by the code, whereas in the very early days, you really needed to do exceptions to the code by doing an alternate solutions process in order to be able to get your local building officials to sign off on whatever it is that you're trying to build out of timber. But that process is getting easier and easier. Appearance is probably one of the big benefits in terms of using timber, as well as the sustainability implications, which have been covered in another video. So what's the difference here between conventional and engineered construction? So conventional construction is kind of the first part of this presentation, which was about light frame construction generally, which generally does not require an engineer as long as it's designed according to the National Building Code Part 9 or the equivalent, Ontario Building Code or other provincial jurisdictions building codes all have some section of the code that is basically for non-engineered timber construction. Okay, so in the NBCC it's Part 9, in the OBC it's Part 9, and this basically gives a bunch of prescriptive rules for how exactly to build something out of light frame timber. So these are how long things can be. This is what kind of, if you have a certain kind of area and you have a certain span, you have to use this beam, you have to do this kind of detailing, et cetera, et cetera, et cetera. So you don't need an engineer because all the engineering details are built into the detailed rules for building that structure. And that's okay as long as your structure is small enough, the height is less than 3 stories, the area is less than 600 meters squared, you don't have super long spans, and you don't have really high floor live loads. So some offices and residential and stuff fall in that category, and then you can just hire an architect and they don't need to hire an engineer. That is not the type of construction that we're interested in this course. Since we're engineers, we're interested in how do we learn how to do the engineered kind of timber construction. Now that could include lumber, could include light frame types of elements. It could include light frame shear walls. Just maybe the building is bigger, maybe the building is taller. But also it includes heavy timber, really large timber elements, whether they're lumber elements or whether they're glulam elements or whether we're talking about CLT, although we're not covering explicitly CLT in this course. You can take the knowledge that you learn in this course and then apply it to those concepts, apply those concepts to CLT construction later in practice or in graduate school. So that kind of construction, basically anything that's heavy timber, anything that's light frame but bigger than those requirements on the left, they all require an engineer with an engineer stamp. And those are the things that we are going to do. And those things are not covered in Part 9. Those requirements are covered in the timber standard, the wood design standard 086 in Canada. So right now in Canada and around the world, we're kind of undergoing like you could call it a wood renaissance. Like timber construction is really coming in vogue, and there's a lot of people looking to do interesting things in timber construction. So I've compiled some slides here just to give you some examples that might give you some ideas of where you can go in the future, some impetus for why we want to learn the things that we're going to learn in this course, because maybe when you go out and do design in your career, maybe you'll have it, some opportunities to design some things that look like these. So this is one that has been around for a little while now, but is a very famous example of innovative timber construction, which is actually a hybrid building, Earth Sciences building at University of British Columbia. And this building does have the lateral load resisting is not timber, but a lot of the gravity load system in a lot of parts of the building are timber, and you can see some really nice tall columns and window mullions and post and beam on the left, and this really snazzy feature staircase, which is actually cantilevered out from the edge of the stair. So this is where it's connected here, and it's connected down here, and out from here and then back is just a big cantilever. So there's no vertical support out here. And this is all made of CLT, connected with innovative kind of perforated steel plates and epoxy. Really cool looking. This is TELUS Soccer Stadium at the Université Laval. And you can see the huge curved, beautiful glulam beams supporting this roof. So it's an arched roof. You can see the abutments for the roof arches here out of concrete. And this kind of thing is not too difficult to design, actually. Curved glulam is covered in the standard. We're not going to cover it in this course probably, but it's not so different than designing beams and columns and stuff like that. Very nice. Here's a really neat one from Surrey with actually these aren't arches anymore, right? They're kind of sagged beams. So not super efficient, but very, very visually striking, and just big, huge glulam beams making a very striking kind of roof. you can see the steel lateral load resisting system in the back here. This is CESM soccer stadium in Montreal. And you can see this is a really neat roof with long, I believe they're probably glulam beams just going straight across with all these diagonals, which I think probably also serve a structural purpose in terms of in-plane bracing of the frame, and also probably yeah, basically making this act more as diaphragm probably. This building from the outside looks really weird, kind of like a spaceship if you Google it. Here you can see some nice timber trusses. There's a lot of examples of nice timber trusses, which always tend to look kind of better than steel trusses just because of the material, but a nice combination. Here are these have hidden connections inside, so the steel is actually a knife plate connection. So there's a slot in the member. So if I have my cross section here, there's a slot cut in the member, and then the steel plate is inserted in the slot and then connected to form these joints. Another really nice thing to do with timber trusses is to put the steel on the outside, and if you paint it black and you just have these kind of steel plates in the corners, they also look really nice. So this is a nice example of a really long span roof structure made of timber trusses. This is a Cree Cultural Institute in Rouget-Bougamou, Quebec. Looks like I forgot the QC on there. But this is a nice timber arch structure. Probably a lot of nice aesthetics obviously put into the consideration of how to make this this structure. Timber arches and stuff, again, it's definitely not rocket science. It's very doable to design structures like this, and the nice thing about glulam is that it's fairly easy to construct into whatever kind of curved shape you like. This is one of the biggest CLT structures in the world, which is called Dalston Works in London, UK, and it's kind of a funny example because the whole thing is made of timber, but you can't see any timber because of this masonry veneer that they've got on it. So it looks like a very run-of-the-mill, pretty boring building. But the nice thing about that is it's an indication that this type of construction has gotten to the point where it's economical enough that people don't care whether you can see it for the aesthetics or not. So it's just, you know, we did it because it was a better way to do it, not because of some kind of special aesthetic requirement that we had. This is a really tall timber building in Norway, and all these braces are all wood. You see these braces down here, you see braces down here, and these braces go all the way up. So they've got kind of an interior structure of pods that are the living spaces, and then on the outside they've got this timber kind of diagrid structure on the outside, providing lateral support, which they have left exposed using these windows so that you can actually see that it's timber. This is a nice Canadian example, which is a structure that's made completely out of timber, which is the Wood Design Innovation Center at University of Northern British Columbia. So this is a university building. This is where they have their wood design program, which they have kind of a neat master's program exclusively in wood design. This building is made entirely out of timber, and even these black bits out here are timber. They're like they're singed panels. So they've kind of burned the outside, which provides kind of a better resistance to the elements and gives a very nice look as well. This is what that building's construction looks like. So you can see the internal lateral force resisting system, which is the core and the elevators and everything, is made out of timber CLT. And then the outer structure, the gravity frame, is built out of timber beam columns, CLT slabs, including a wood envelope. So like this is a very showcase project for wood construction in Canada. I encourage you to look more up about it if you're interested. Brock Commons, we already talked about quite a bit, but this was definitely the tallest timber structure in the world at one point. I'm not sure if it still is, but I think it's 17 stories. So it's definitely one of the tallest timber structures in the world. Timber can also be used for bridge construction, and there are quite a few nice examples in Canada. I've put a couple here. These ones are both from Quebec. You can see the really nice curved glulam and glulam girders. They might actually not be glulam. I'd have to look that up. They don't look like glulam, but they are definitely some kind of engineered wood product. And of course, the greatest concern here is going to be for drainage, so that you make sure that since it's an outdoor structure with exposed wood, that wherever the water gets to, it doesn't pool and stay there for a long time so that you get rot. So that's probably was one of the main design considerations of the designers of this bridge. Here's another really nice example with long curved arch picking up this roadway bridge in Quebec. So those are all the examples I have for wood structures, and I think that we reviewed a lot of neat structures that exist and what's the future, and also what kind of wood structures you can look at designing yourself in the future.